Hello everyone, welcome to the class ECE317 Digital Signal Processing. Today is the 13th week, Monday's class, right? ECE317. We could keep working on the system edge of Z. This is a transfer function. We have input X and we have output is Y. If input is a sinusoid, so okay, I write in more generally is e to the j omega 0 n. So this is the combine of both cosine and sine, right? Is it this one? Okay, if x is this one, then y of n will be h of his frequency response at the frequency omega 0, right? E to the j omega 0 times the input is e to the j omega 0 n. Right? We have this one. If we write in terms of if x of n is cosine, just cosine, then we have y will be magnitude times cosine of omega 0 n plus the angle of h, angle of the frequency response, right? So we can write in this way. And if x of n is a sine, that will be similar. We have y of n equal to magnitude of h e to the j omega 0. Now here's a sine. Okay, inside is also same with this case, with the cosine case, right? Same with cosine case. Here's a plus the phase angle. Alright. And actually this one we can also write it as magnitude of h times e to the j omega 0 n plus the angle of h. Alright, if we write it in this way, then these three, they are in the same style. The amplitude is changed by h with magnitude, and the phase angle is changed by the angle of h. And this part omega 0 n plus the angle h of e to the j omega 0, we can write it as omega 0 times n minus negative, here's omega 0, denominator and numerator is angle of h. Right? They are same, right? They are same thing. You remove omega 0 outside, then this is omega plus the fraction angle of h over omega 0. But I need a minus. If we write in this way, this part, negative angle of h over omega 0 is the time delay. Right? It is a delay. The delay n by this element. But here we have something about a discrete time signal you have to know. This is not really a time delay. Sometimes it is time delay, but sometimes it's kind of time delay, because for discrete time you need these to be integer if it is really a time delay. If it is not integer, it is some number errors, then this kind of delays happen in the continuous times case. For discrete time signal, it is not really a delay, but the meaning is the same. We use an example to see the difference between these two. example, The first one I use h of z is 1 over 1 minus half z to negative 1. I think last time I used this one, right? And x of n is a cosine signal with omega 0 n, which is omega 0. I choose omega 0 as whatever, just like a pi over 2. Is that right? Yeah, pi over 2. Pi over 2, the xn will be, this is cosine, right? Cosine. Pi over 2, we will have examples like these examples, like this, right? We have 1, 0, negative 1, 0, positive 1, 0, like this, right? This is x of n. Then what is y of n? Y of n will be magnitude of h of e to the j omega 0 is pi over 2 times cosine of omega 0 is pi over 2 n, and plus the angle of h e to the j pi over 2, right, like this. And for these two numbers we can calculate. Yeah, you can, if you want, you can also calculate by your hand, but we have this way, right? We can save our times. That is 1 minus 1 over 1 minus half times exponential power of negative. Now z is e to the j or negative j, e to the j omega. Negative 1 should be, right? It is this one, right? We just replace z by this one. So e to the negative j times pi over 2. Pi over 2. Okay, so this will be h. I say just say h equal to this one. H equal to this one. Then absolute value of h, the magnitude of h is 0.8. Okay, right here. It is a 0.8944 times cosine pi over 2n plus the angle of this h, disappear. Angle of this h is a negative, or it's a negative one. It's a, okay, the document camera shut down. Oh, maybe because I touched the USB. I lost it. Oh, sorry. Waiting for a while. Okay. We need to turn around. Okay, now the phase angle is minus 0.4636. So y of n should be this one. Alright, y of n should be this one. So we can have y of n. We can have a y of n. Okay, now let's see the graph of it. Y of n. Okay, I need to compare. I want to compare x of n and y of n. How do they look like? So I use n round from 0 to like 20. I take 20 samples. Then xn will be cosine of omega 0. I put the omega 0. Omega 0 is pi over 2. Then xn equal to just cosine of omega 0 times n. Okay, this is x. And y of n will be the absolute value, magnitude of h is 0.8944 times cosine of still pi over 2, so it's omega 0, right? Omega 0 times n minus that phase angle is 0.4636. Okay, so this is y of n. Now let's plot xn, yn. No, I need 2. N and xn. So n is a kind of the time, right? And time and yn. Alright, I have these two. What can we have? Now we have two curves. That blue one. Okay, this is discrete time. Can I use them? Apply stem. Oh, it doesn't work. Let's just plot. Okay. Plot. So by the plot, the blue one is x of n. Then the green one, the magnitude is somehow smaller, right? Magnitude now is 0.89. So this is the magnitude. So it should be a less magnitude, less amplitude, the green one. But it is not really a shift. The original one will be the blue curve, right? You see the blue curve and the green curve, are they really a shift? No. If you just like to look at the graph, they didn't look like a shift. But how do we say this is a shift? Okay, you need to check the signal behind this discrete time signal. I need a t. T still run from 0 to 20, but with a small step. This is t. Then I have xt. Xt is cosine of, now is omega 0 times t. So this is a continuous time signal. X of t. And yt is also a continuous time signal. Here's y n, and make some change here. This is yt equal to magnitude. This is omega 0 t, and the phase is the same. Okay, this is x of t. Now I plot all of them. I have t and xt, t and yt, and n. Okay, n I use a circle for the x, and yn I use a diamond. Okay, I have my graph. Alright, this time it looks better, right? We have the blue one with red circles. They are the original signal. X of t, x of n. X of n is the original signal. X of t is you can think it's the signal behind the discrete time signal, right? We have a continuous time signal, and those circles you can think it's a kind of symbols from the blue curve, right? And then we go into the system. The output will be this diamond, these green lines. So if you compare the blue line and the green line, these two curves, these two waves, they are shift. There's some change on the amplitude and with a shift, right? With a shift. However, if you just look at the diamond and the circle, the diamond are here, this blue diamond and red circles, they are not really looks like a shift, right? Like a shift, like this blue one. If it is shifted to some diamond, no, it's not shifted like this diamond. Right? This diamond is different. Actually, they are these curves are shifted. But if you just look at the green and the blue, there's a green diamond and the red circles. They looks not really a shift. All right, so you should understand what does the meaning of a shift. Right? What is the meaning of the shift in a system? As an output, you shifted the input, so you shifted in this way. The background analog signal was shifted, but you just check the samples, check the discrete time signal, and it looks like not really like a shift. Yeah, we can also just look at the without the T, just the X. Okay, you see, it look like this. The blue ones, the green, blue circles, they are the original signal. 1, 0, -1, 0, +1, 0, and the diamond here, like a 0.4, -0.8, -0.4, 0.8, -0.4, -0.8, right? It run like this way. They are not really a shift of the original signal, but we say it is a shifted. Alright, okay, so this is what happened. If the phase angle here, we can think it's a shift, but this shift is not a constant, not an integer. Right out what is a shift? It's a 0.8944 times cosine. Here's a pi over 2 times n minus 0.4636 over pi over 2, right? So this shift by this number. What is this number? This number is 0.4636 over pi over 2. Okay, this is shifted by 0.2951. Right? Shifted by this. So the graph looks like this. The one shifted by 0.29 something should be somewhere here, but we do not have example here, because our example, we have to have our example at the time n equal to 1. The first example, n must be 1. But the signal you want to shift just a little bit, then you cannot have really example at this place. You know, we cannot have sample at this place. My mouse is moving, right? We can have sample where we one more times later until n equal to 1. Right? Okay, so this is one thing. All right. Okay, this is one example. Then we can consider another example. We want with integer delays. Let me h of z. I think I have some example last time. Anyway, I give new one more. It is a new one. Give new one. 1 plus 3z to -1 plus z to -2. I use h of z, this one. And xn, the same xn. Xn is still cosine omega 0 n with omega 0 equal to pi over 2. I will still use this one. Then the output side, we know we need to calculate the magnitude and the phase of these two, right? So we have h of e to the j omega 0, this one, equal to, alright, we can calculate it. It will be 1 plus exponential power of, actually this one is 1 plus 3 e to the negative j omega 0 plus e to the negative j 2 omega 0. Right? So this is a 3 times exponential power with, here inside is a negative j times omega 0, which is pi over 2. Okay. And then plus another exponential power with negative j times 2 times omega 0 is pi over 2. Mind you? Okay. Oh, it's a negative 3j. Okay, this one is a negative 3j. 3j. I use j for the square root of negative 1. 3I, doesn't matter. Okay, then the magnitude. It is a magnitude of negative 3j. It is just 3. Just 3. And the angle will be, you can see here, negative 3j is here, right? So the length is magnitude, it is 3. The length is 3. And the angle will be negative 90. Right? So it's negative pi over 2. This is the angle. Okay, so we have y of n equal to 3 of the cosine of omega 0 n and minus pi over 2. Alright, so okay, you can see how the graph looks like. Now xn is cosine omega 0 is changing. I change omega 0. Omega 0 now is pi over 2. Or didn't change, the same thing. Yeah, xn is still that xn. Xn is still that xn, and yn is changing. Now the magnitude is changed by 3. Right? And the phase angle is minus pi over 2. Actually, pi over 2, then we write one more. This is 3 cosine. Pi over 2 is just omega 0, right? So it's n minus 1, like this. Okay, it's shifted by 1, right? Shifted by 1. This is n minus 1. This is yn, xn and yn. Then let me plot x and y. Oh, they merge together, you see? They merge together. Not merge together. They have some up and down. Okay, I still need the background curves. I give the continuous time signal that is xt are same, but yt is changed. Yt is 1, here is 3, and shifted by minus 1, right here. Yeah, or pi over 2, just pi over 2, just pi over 2. Okay, so this is yt, and let us plot this one. So I have both. I have already signal in the, yeah, we have this one. Okay, now the blue curve is the original one. Those circles, red circles, they are x of n. And the green one is the output side. It is shifted by 1. You see, here's 1. This peak location is time is 1. So the peak shifted to 1, shifted by 1. The magnitude is 3 times, so now it's 3, right? So the green one is shifted, blue one with 3 times of the magnitude. And the symbols, it is also shifted by 1 with change on the magnitude, like this one here. N0, we have value 1. The input signal is 1. The output signal, this one will occur at time 1, shifted by 1. When time is 1, we have the peak value, and this peak value will be 3 times of the input side, so it's 3. Then like the next value should be 0, right? Input side, when n is 1, the input signal is 0. Then output signal at time 2 is shifted by 1. Right? You will also have the same value 0, or 0 times 3, that will be same thing. Okay? Yeah. So in this example, the output signal, it is really a shift of the input signal by 1 and then times 3. on the magnitude, on the amplitude, right? This is really a shift. In the discrete time sense, it is also a shift. So compare with the first example. In the first example, if you check the signal in the continuous time domain, it is a shift. If you just look at it in the discrete time domain, in the discrete time case, it looks not really like a shift. Right? But this example, both in time domain and both in the discrete time case or continuous time case, they are shifted by the same step 1, right? Shifted by 1. Yeah, this is the reason. It's shifted by an integer, so these two, they will be same. Yeah. If it's shifted by a non-integer value, then in discrete time sense, it might be looks not really like a shift. Okay, so this is a shift. All right, now we consider system. We consider a kind of system called linear phase system. Linear phase system. That means the angle of edge of e to the j omega were equal to some constant, I say r times negative r of omega, like this. Satisfy this one. The angle is this one. Angle is negative r times omega. Then I will say this negative r will be just a positive r will be the time delay no matter what is omega 0. Alright. Okay, of course here we consider the same thing. We use x of n input, then we have output, and the next one will be a sinusoid. It is cosine n omega 0 or e to the j omega 0 n, or a sine of n omega 0 omega 0 n in this case. Then the output side, I just give output with this one, right? These two will be similar. The output side, it will be magnitude of h times cosine n omega 0 plus, okay, this is negative r omega 0. Alright, this is negative r. Okay, then this one we can write is a magnitude of e to the j omega 0 times cosine of omega 0 with n minus alpha here. So this is shifted by alpha. If alpha is an integer, this shift will be really shift in a discrete time sense. If this is a non-integer, some other numbers, this shift is it will happen in the cosine behind the analog signal behind this discrete time signal. Right? Okay, so we have this one. So by this way, no matter what is omega 0, right? For different omega 0, we have same shift. So this property give us the feature. When you have input in the output side, if you have signal with different components with different frequency, then output side, the different frequency, they were delayed by same time. If we do not have these, then different components were delayed by different time. Then that's different, right? That's different. So here we suppose they're like this one. So we call this a linear phase system. Right? The phase is some constant negative alpha times the omega. It's a linear phase. And for linear phase, the output signal, it is just shifted by this alpha, no matter what is the frequency. No matter what is the frequency. It's always shifted by alpha. It's always shifted by alpha. Okay. can have look like which example we can have this one. Yeah, this one will be same thing. It's just like this one. We know this shifted by 1, right? This shifted by 1. The omega 0, now omega 0 is pi over 2. If we change the frequency, Example, let me write it here. Now is h of z is 1 plus, what is that? 1 plus this one. 1 plus 3 plus 1. 1 plus 3, z to negative 1 plus z to negative 2. And the input x of n is cosine omega 0 n. We have tried omega 0 equal to pi over 2, right? Now we can try different, like a 1, like a 2, whatever happen. Yeah, just 1 and 2. Then here I make some change. Xn equal to, I just change omega. Omega 0 is 1. Yeah, I can put it in a function. Alright. Put the function, I put it in 317. Okay. Edit. This is a lecture for 13 weeks Monday. Okay, let me edit this one. Can I copy this kind of things here? Okay. I have xn, then I put this yn, and I plot. Apply this one. I have yt. Okay, before that we need a n. N run from 0 to 20, 1 to 20, 1 to 20. This is x of n. 0. We can start from 0. And run from 0 to 20, and t is also from 0 to 20. But we need a step here. So this is for continuous time. And that is discrete time. For continuous time, I also need x. Xt is x is a cosine of omega 0 times not minus times n times t. Okay, so this is a then the shift will be different. So shift will be shifted by angle. I say angle of h. Alright, this angle of h. And this will be the magnitude of h. Alright, then I can plot all of them. And of course, before that, we didn't know what is omega 0. Omega 0, I use pi over 2. This is the original one. Now I want to try omega 0 is 1 or 2, right? I put the 1 firstly. And then use this. Okay, then I also need the magnitude and the angle of the frequency response, mh. So mh will be calculated here. So I need h firstly. H will be 1 over 1 minus 0.5, the half, times exponential power of negative j times omega 0. Am I good? I think it's good. This is h. Then we have the mh MH will be, oh no, different H, sorry. Different H. H, second one, it is 1 plus, this is this one. This is this one. It is 1 plus 3 with, here's omega 0, and here's a 2 of omega 0. Then MH is the magnitude, right? That's value of H. This is the magnitude and the angle of H. Angle of H. Angle of H will be angle of H. Okay, am I good? So far, here. This will be not 3. This will be magnitude of H. And here will be minus angle of H. Okay, it seems good. Let us try the pi case. Sorry, try this case first. If it works, it should give us same result, right? Okay, save to. Okay, save and run. Where's the result? Is here. Why is it a straight line? I get something wrong. Should be cosine, right? Oh, this is t. Here's a dot. Okay, try it. Yeah, now it's good. Right. This is the case. Omega is pi over 2. Now we consider omega 0 with different 1, like omega is 1. Okay, now the graph is different, right? Graph is different. Is it shifted by 1? Let me see. This signal now is a peak value. Now peak value will be on the top. Oh, it's not different. Not in the top. Am I good? It should be shifted by 1, right? Angle at, oh, here's plus. Sorry. It should be plus. Yeah, now it's good. Yeah, this time is good. This time is good. The peak value here is 0, right? You see the first point. When n is 0, you have peak value. This is the input side. Then the output side, this peak value go out of this here. N is 1. Then we have another peak value. This is 0, 1, 2 to be here. For n is 3, we have a negative peak, right? Then shifted by 1, when n equal to 4, we will have, oh, this is not really 4. Okay, this is kind of calculation. The some error in the calculation. Yeah, oh, I don't need this. I don't need this. So can we reduce that errors? Yeah, when the time is large, we have large errors. Yeah, this is because the omega 0 is is 1. Okay, I use some pi over something, pi over like 6. Yeah, this time it will be good because the 2 pi is a period, and that makes things errors because pi you have after pi is an irrational number, right? And after dollar you have infinite number, so use pi. Now I use pi. I use integer that is different with pi is not good, so I just use pi. Some integer time, some part of pi, 1/6 pi. Oh, this one. Yeah, this is a shift. Yeah, this is shift. You see, the first peak shifted by 1 to second to here, right? And then the negative peak shifted by 1 is here. Is also negative peak. Then here's in the blue. This one is a peak again, and shifted by 1. Here's another peak. It always works like this. Okay, so now this is good. This is good. So output side and input side, they are really a shift. Shift at the times this value should be 4 dot something. Did I show it? Oh, I show h. I don't want h. I want the absolute value of h. So absolute value of h and the angle of h. Then we can see what are the values of magnitude is 4.7 times, and phase is -5 to -7, 4.7. So this point should be 4.7. 4.7, and here's another 4.7. So this time it is really shifted by 1. The input signal shifted by 1, and then make a scale change on the amplitude. You can have output. And if we change the signal, change the function h, now they change the transfer function h to be a different one. Like change to this one. I change it to this one. I change it to this one. It will not be shifted by 1. Oh, look like this. You see, this peak value. This point is not really a peak. It is a little bit different, right? Here's one more different. This is not really peak value. You change a little bit, but input side, this one is in the peak, right? If you shift it by 1, it should be in the peak, but now it is not in the peak value. Yeah. So this is the case for that one is not integer. Yeah, we can also see the angle over omega. What is the angle over omega? This is the angle, and the angle over omega 0, and with a negative. This will be the delay. This will be the delay. Okay, now this delay is 0.79. So you cannot really have this as a delay. And if we go to different example, like I go back to this one. This one is I have integer delays. If I use omega 0 with different one, like I use 5 times it. 5 times it. What will happen? Oh, like this. Yeah, it's also shift, right? Peak value here, then shifted by 1. Input is a peak at 0, and output the peak at 1. Then next value is here, then shifted by 1, you get this value. Then this value shifted by 1, then change on the magnitude, right? Any point, like this point, shifted by 1, and the change on the magnitude, you get this one. So this is a shift and scale on the amplitude. Okay, so in this example, this one, we have y of n. It is always h of e to the j omega 0 magnitude times cosine of omega 0 of n shifted by 1. Always delay by 1. It's a delay, right? Delay by 1. Delay by 1. And H, the angle of H, it is always negative omega. Always this one. Always this one. So we just calculate. We can calculate it by this way. Why? Is H of Z, H of e to the j omega, it will be 1 plus 3 e to the negative j omega, right? You just replace Z by this one, and plus e to the negative 2 of j omega, right? Go to this one. Then I remove e to the negative j omega outside. Then inside will be e to the positive j omega plus 3 plus e to the negative j omega. Right? This is I have 2. Remove 1 out. Here I do not have. Then I put the positive 1. All right. This one is a cosine of omega plus j sine of omega plus 3 and plus this one is a cosine of omega minus j sine of omega. And all of these we times e to the negative j omega. Yeah, right here. I do not have space. Then, okay, here you see cosine plus 3. So here's a 3 plus 2 of cosine omega. And these 2 they cancel, right? Plus and minus cancel. So we have only these 3 terms times e to negative j omega. Alright, so this part is h of e to the j omega with a magnitude. And this part, this is the angle of h of e to the j omega times j. It's like this. Like this. So the angle now is negative omega. That means alpha is 1. Alpha is 1. See, I give you the alpha right here. Sorry, switch page. Yeah, here. And you see, angle of h is negative alpha times omega. Now is angle of h is negative alpha times omega, right? Alpha times omega. What is alpha? Alpha is 1. Alpha is 1. And it is shifted by 1 in the upper side by this alpha. If input is a cosine or sine or any sinusoid, right? Shifted by 1. And this one we can also see the graph of this. It will be a okay. This is a figure 1. Figure 1. Figure 1 is to give the plot of the input and output signals. Now figure 2, I want to plot h, omega and maybe s of h. I want to plot these. To plot these, I need a w equal to, we only need this from 0 to pi, right? To pi. We only need these. And now h will be the still this one, but we have now the h is not h0. H will be h will be related with the whole omega, not just for omega 0. Okay. Then I plot this one. And I also need to plot the w and the angle of h. Before that, I put these 2 together. This is figure 2. And subplot 211 subplot 2 capital 2. This one F1. Okay, this one figure 2. Figure 2, I have two graphs. The first one is the magnitude of the frequency response, and the second one is the phase. Now you see the phase angle. You look at it in the graph, it will be straight line. Alright. Yeah. So this kind of things we call it as a linear phase field, linear phase system. Okay, that's all for today. Let's see you next time.